So before I get into all of this stuff that I have here, I want to give a little bit of motivation for why I might care about the central limit theorem. And for one, very straightforward reason, when we talk about all these patterns that we've seen in chapter 5, and a lot more that we're going to see in 6 and 7, there's kind of an assumption of normality. Because there's a lot of data that happens to be normal. We talked about that at the beginning of the chapter. But there's also a lot of data that isn't, and for that matter, shouldn't ever be expected to be normal. There's a lot of times you don't get those nice patterns. For example, coin flips should not have a normal distribution because you only have two options. At best, you get something that's very symmetric and uniform, but that's not a normal distribution. And for that matter, sometimes when we're talking about these data behaviors, we may not just want to know about a single point. We may want to be able to say something about an overall pattern. We may want to be able to say something about what happens on average with our data set. And these two cases are why we have the central limit theorem, where to be exacting with our definition, the central limit theorem says that for samples of size n at least 30, the sampling distribution of sample means approximates a normal distribution, where the approximation improves for larger samples. And on the other hand, if the population is normal or approximately normal, then the sampling distribution of the sample means is normally distributed for any sample size. So essentially that first case says that we can have any pattern we want, any nasty mess of data, but if we take properly sized samples from it and talk about the means of those samples, we'll get something that ends up being approximately normal. And then on the other hand, if we want to talk about sample means, if we want to talk about sample behavior, it doesn't matter how small or how large of a sample we take. If we're dealing with approximately normal things, we can just take that it is approximately normal, that our overall behavior is going to work well enough. Where for this, it's important to know that the distribution we're working from here isn't the exact same as the distribution for our data. That is, it isn't based on the exact same patterns, the exact same parameters. When we're using the central limit theorem, we have to take into account the fact that we're not just talking about a mean of values. We're talking about a mean of sample means. We're talking about a mean of means generated by samples of the same size, where that is denoted mu sub x bar, but for our purposes, mu sub x bar happens to be equal to mu, or at least it's approximately equal to mu. It's close enough that we can take it as our estimated value. But on the other hand, when we're talking about standard deviation, let's think for a second. If you're taking single values, it's always open to the possibility of getting a bad number or getting some strange thing in there that makes it unrealistic, that throws it off, that there's always room for variation with single things. But when you're talking about overall large macro behavior like means, especially repeated means of the same size, you should expect that there's not a whole lot of room for change. You should expect that there's not a whole lot of that room for variation, because if you're stacking, say, 30 things together many times, that distribution is going to get pretty narrow. So, when we talk about the standard deviation, we instead have a term called standard error, sigma sub x bar, where sigma sub x bar is the value sigma divided by the square root of n, the square root of the sample size that we're working from to generate our sampling distribution of sample means, where if n equals 1, if we take things of size 1, well, we're just taking data points again, so it just ends up being sigma. But generally, the larger sigma gets, the smaller the value for sigma sub x bar, the standard error, will get. And that should make sense. We take larger samples, we should get less variation, so our measurement of variation should get smaller. And that's essential. It's essential to understand that what we're doing here is we're shrinking our variability to account for the fact that we're taking in more things at once, as it were. And to understand this a little bit better, we're going to look at an example. So for this example, we have that a study analyzed the sleep habits of college students. The study found that the mean sleep time was 6.8 hours with a standard deviation of 1.4, which I think is definitely not enough for your growing minds, as it were. But random samples of 100 sleep times are drawn from this population, and the mean of each sample is determined. We want to find the mean and standard deviation of the sampling distribution of sample means, then sketch a rough graph of that sampling distribution. So here, we're not exactly computing these things just in terms of probabilities yet. We're talking about how we can make that conversion first to talk about our parameters properly. So one other thing that we have to bear in mind is that when we're looking at things like z-scores here, we're not talking about z-scores for single values. We're talking about z-scores in terms of mean behavior. So here we have z is equal to x bar minus mu sub x bar divided by sigma sub x bar. That is, we're talking about the distance from a single sample mean to the mean of sample means divided by the standard error, the standard deviation of our sample means. I'm going to get this deviation and distribution backwards at least one more time here. Sorry in advance. But anyway, we can use the central limit theorem, where the central limit theorem in this case holds because we have 100 elements in our sample. It doesn't matter what distribution the sleep times follow, whether it's normal or uniform or skewed or what have you. Because we have enough information, we can talk about the distribution of sample means and know that that will be approximately normal. So, using our approach here with the central limit theorem, we will have that the value here for mu sub x bar is just our population mean mu, at least approximately, which is 6.8. Meanwhile, the standard error, sigma sub x bar, is going to be sigma over the square root of n, where here sigma is the value 1.4 divided by the square root of our sample size, which is 100. So it's 1.4 over 10, or 0.14. So if you want to think about what this looks like as a distribution, we'll see that we have an approximately normal distribution, but it is an incredibly thin distribution, that there's not a whole lot of room for variation when we're taking in that much information every single time we want to talk about a value that is a sample mean with 100 things in it. As you might expect, if you're going to draw 100 things every single time, you shouldn't expect there to be much change from one to the other, because you're probably going to get a lot of the same data in both of those samples. Unless you've got millions of people, but even then, you've still got a lot to pick from. And you've still got a lot of space for that variation to get ground down to a very fine point, like here. And next, we're going to look at how we can do this stuff, how we can take these things another step to actually start looking at probabilities in terms of these values. Because if we have approximate normality in terms of these parameters, we can talk about finding probabilities or finding values given areas in the exact same way we did the first few sections of Chapter 5.